AP Calculus AB test, limits and continuity. Last week we had a test on limits and continuity, and so this is a video lessons, a review of that test. Using the graph of h of x, answer problems 1 through 6, 1 point each. So 1 is the limit as x approaches -3 of h of x is. Well, the limit is found by if the left side limit is equal to the right side limit. So if we approach 3, and here we have 3 on the x-axis, as we're going here on the graph, as we approach from the left side and from the right side, these two opposing arrows, we're approaching the output value of -2. So the limit is what number is being approached, not the number itself necessarily, which we're going to look at later on. Problem 2, f of -3 is if we go to the value of -3, well, there's a hole down here where the limit is, but if we go up here, we see this point at whose value is 4. So f of -3 is 4. So this at x equals -3, we do not have continuity because the limit, which is -2, does not equal the value of the function, which is 4. Problem 3, the limit as x approaches 2 of h of x is, well, here at x equals 2, from the left side, we are approaching the number 1, and as we're approaching the right side, we're approaching the value of -3. So left-hand limit, which is -1, does not equal right-hand limit, which is -3. So therefore, our answer is that our limit does not exist. And then we can, if you have significant work shown, I like to see the answers boxed in like this as a symbol. This is my answer. Okay, number 4, f of 2 is, and so we go to x equals 2, and this point here defines that x, the value of f of 2, is going to be -1. Now the limit as x approaches 4 of h of x, and so here we are at x equals 4, and so from the left side, we appear to be approaching here, and the right side here, so we appear to be approaching this value, which is going to be, looks like -1. And f of 4 is going to be that same thing because there's just an unbroken line segment. So -1 is our answer to f of 4. So this is an instance where your limit equals the f of that function at that value, which is 4. So that's the definition of continuity. 7, 7 and 8, couple tables. Limit as x approaches 3 of g of x is, and so we have here these values of x from the left, 2.9, 2.99, 2.999, 2.9999, and then eventually to 3 from each side. So we're approaching 3. As we come from the left, what number are we honing in on from the left? Well, we're honing in toward 1. But we come from the right, we get 3.1, 3.01, 3.001, 3.001. What are we approaching from the right? Well, we're honing in on a number -1. And we have a left side limit, which is 1, not equaling a right side limit. And so since the left side limit does not equal the right side limit, we say that the limit does not exist. Problem 8, the limit as x approaches 1 of f of x is, and we can see on this top row we have 0.5, 0.9, 0.8, 0.9, 0.99. So we are approaching 1 as we go from lower to higher. As we come from higher to lower, 1.5, 1.2, 1.1, 1.01, we're also approaching 1. But our limits, as we come from the left, we are approaching 4.02, 4.02. We are approaching 4 from the left side, and from the right side, we come to 4.0, 4.02. We're approaching 4. And so the left side limit equals the right side limit, and that is the limit. So our limit is 4. Our limit is not 3. 3 is f of 1 is 3. So this 3 is an anomaly. So we're talking about a discontinuity, which would probably be a point discontinuity, but the function will be defined at x equals 1, but will not equal the limit. So those would be our answers for 7 and 8. And in 8, I think most people had trouble with that. Okay, next set of problems. Determine each of the following limits, show your work, and simplify your answers where applicable. And let's look at these. Okay, first strategy in limits where you're approaching a number as x approaches a number that's not infinity, right? What we'll do is we're going to plug in. And so here we have the limit as x approaches 2 of all this. And so if we plug in, I'm going to work that below here to leave room for the answer. Okay, we have 2 minus 2 in the denominator, which is going to be 0. In the numerator, we have x squared, which is 4, which is 2 squared, which is 4, plus 3 times 2, which is 6. So 4 plus 6 minus 10 is 0. So we have 0 over 0. And so what we're going to have to do is factor. See if we can factor. So if we factor, we have in the denominator x minus 2. In the numerator, we can assume that one of our factors will probably be x minus 2. And our other factor, if we have one of them x minus 2, is going to be x plus 5. And x minus 2 over x minus 2 cancel. So what we need to do is substitute in 2 into x minus 5. Well, x plus 5. So 2 plus 5 equals 7. So 7 is our correct answer to problem number 9. Problem number 10. The limit as x approaches negative 2 of x squared plus x minus 2. And so that's going to be, we'll just replace x with negative 2. So we're going to put negative 2 squared plus negative 2 minus 3. And negative 2 squared, that's going to be 4. So we're going to have 4 minus 2 minus 3 is going to be equal to negative 1. So negative 1 is our answer to problem 10. Problem 11. The limit as x approaches 1 of 5x minus 5 over x minus 1. And so if we substitute in 1, we're going to have in the denominator 1 minus 1 is 0. In the numerator, we're going to have 5 times 1, which is 5, minus 1, which is 0. So we have 0 over 0. So we're going to go ahead and try to factor. And we have in the denominator x minus 1. In the numerator, we're going to have also x minus 1. We have to assume if that's cancelable. And what number do we have to multiply by quantity x minus 1 to equal 5x minus 5? We're going to have to multiply 5. So we cancel out this x minus 1 over x minus 1, and we're left with 5. And so now if we plug in our value of 1, but there's no variable to plug into, right? So the thing's just going to be 5, period. So 5 is our answer to problem number 11. Problem number 12, we have limit as x approaches negative 4 of x plus 4 over x squared minus 16. Well, we're going to have for that in the numerator, we're going to have negative 4 plus 4, which is 0. In the denominator, we're going to have x squared, which is negative 4 squared, which is going to be 16, minus 16. So we're going to have 0 over 0. And so what we're going to have to do is see if we can factor, simplify. So we're going to have in the numerator x plus 4, and in the denominator, we're going to have a difference of squares. X squared minus 16 is going to be quantity x plus 4 times quantity x minus 4. And so x plus 4 over x plus 4 cancel, and we're left with 1 over x minus 4. And then if we substitute in negative 4, we get 1 over negative 4 minus 4, which equals negative 1/8. So negative 1/8 is our answer to problem number 12. Problem 13, limit as x approaches negative 2 of x plus 10 over x plus 2. So anyway, to plug in, we're going to take negative 2 plus 10, which is going to be negative 8, and actually be positive 8, isn't it? Negative 2 plus 10 is positive 8. And then in the denominator, we have negative 2 plus 2, which is 0. So we have 8 over 0, which equals infinity. Therefore, our limit does not exist. And if you put just infinity as your answer, that's not a correct answer. The correct answer is does not exist, really. 14, we have the limit as x approaches 6. And so for that, we're going to have let's take a look at this. X approaches negative 6. So we're going to get negative 6 over negative 6 plus 6. We're going to have negative 6 over 0, which equals negative infinity, which again, we conclude that the limit as x approaches negative 6 does not exist. Problem 15. Limit as x approaches 10 of x minus 10 over x. So what that's going to be is we have in the numerator, we have 10 minus 10, which is 0, over our denominator, which is 10, and 0 over 10 is equal to 0, so our limit is equal to 0. That's problem number 15. Problem 16, the limit as x approaches infinity of x cubed plus 27 x to the fifth over x to the sixth plus 2. Well, this is an instance where we look at the highest power of the polynomial, which in the numerator is x to the fifth, right, to the fifth. At the bottom we have x to the sixth. And so since we have a higher power in the denominator than in the numerator, we're going to have we have a bigger on bottom situation. So our answer to this one is going to be 0. So this means that that the horizontal asymptote for this function is going to be y equals 0. 17, we have the limit as x approaches infinity of x cubed plus 27x squared plus x over 3x cubed. Well, what happens is our highest power is to the third power, x to the third power, and 3x to the third power in the denominator. So compared to these x to the third power, the leading terms, it's like this 27x squared and plus x don't even matter. So our answer is going to be x cubed over 3x cubed. And x cubed or x cubed cancel, so we're going to get a value of 1/3. And 1/3, y equals 1/3, is the equation for the horizontal asymptote of this function. And finally, number 18, the limit as x approaches 3 of x cubed plus 27 over x plus 3. Well, it's going to be 3 cubed plus 27 over 3 plus 3, so it'll be over 6. So we're going to have 27 plus 27, we're going to have 54 over 6, which simplifies to 9. So 9 is our answer to problem number 18. Let's go on to our next set of problems, which is 19 through 21, which has to do with these graphs of the functions f of x and g of x. In this problem 19, we're looking for the limit as x approaches -2 from the left side. And so look at f of x here. We match up f of x, that's this left one. So as we approach -2 from the left side, we hone in on this value here of +2. So that's going to be 2 plus, and then we look at this right one here, the limit as x approaches 5 from the left side of g of x. So we come over to this g of x, and we go to 5 from the left side, and we hone in on this value here of negative 2. So we have 2 plus negative 2, which is going to be equal to 0. So 0 is our answer to problem number 19. Problem number 20, limit as x approaches 1 from the left side of g of x. And so here we are at g of x first. So as we approach 1 from the left side, we hone in on this value here of y equals 3. So we have 3 minus, and the limit as x approaches 2 of f of x. So as we approach 2 of f of x, and that means from both sides. So we have to make sure we're approaching the same thing. So the limit approaches 2 from the left side and from the right side. The same thing will come to a value of 1. So we have 2 minus 1 equals 2. So 2 is our correct answer to problem number 20. Now problem number 21, we have the limit as x approaches 1 from the left side of f of x. And so we go to this 1 from the left side, and we get a value of 1. So we have 1 times, and then we have the limit as x approaches 1 from the positive side of g of x. So as x approaches 1 from the positive side of g of x, we hone in on this value here of negative 1. So we have 1 times negative 1, which equals negative 1. So negative 1 is our answer to problem number 21. Next problem. What's the intersection of the lines x equals negative 4 and y equals 3? And what I was looking for is a coordinate pair. And a coordinate pair has to have some basic components. You have to have two numbers separated by a comma and surrounded by parentheses. If I did not see these things here, oops, that's not going to be 1, it's going to be 3. So we have negative 4, comma 3, y value is 3. And I think I saw 1 or 2 people who didn't put parentheses in place. Got to have parentheses. You have parentheses, the two numbers separated by a comma. 23, find the integral from 0 to 5 of 2 dx. And so we're interested in this function y equals 2. And so here we have a graph here, and at 2 we have that's a horizontal line whose value, this is y equals 2. And then we have limits from 0 to 5, from 0 to 1, 2, 3, 4, 5. So 5 we have right here. So what we have is a rectangle. And we have a rectangle whose width is 5 and whose height is 2. So our answer is going to be 5 times 2, which equals 10. Okay, that is our right answer for problem number 23. Problem number 24, let h of x equal 3x minus 3 for x is less than or equal to 2, and negative x plus 5 for x is greater than 2. So basically we're given a kind of a checklist around this critical value, x equals 2. And so the limit as x approaches 2 from the left side of h of x, that's determined by this top piece where x is less than or equal to 2. So we're going to put this in as 3 times 2 minus 3, which equals 6 minus 3, which equals 3. So our answer to part A is 3. Okay, part B, the limit as x approaches 2 from the right side of h of x, and that's going to be for x is greater than 2. So we're going to take negative 2 plus 5. Well, negative 2 plus 5 is equal to 3. So what we have is we have a limit from the left side equal to 3, a limit from the right side equal to 3. So the limit as x approaches 2 of h of x is 3. Okay, answer A is limit from the left side. Answer B is limit from the right side. And finally, D, h of 2 is, well, we have the function is value is 3x minus 3 when x is less than or equal to. So to find out h of 2, we have 3 times 2 minus 3, which equals 3, which is going to be the same thing as our answer A, really. So it's the same rule for determining h of 2 is the same as determining the limit of h of 2 from the left side. Okay, E, is h of x continuous at x equals 2? Why or why not? And the answer is yes. And then we need to give the conditions. 1, h of 2 exists and is equal to 3. 2, limit as x approaches 2 of h of 2 exists and is equal to 3. So 3, since h of 2 equals limit as x approaches 2 of h of x, then you put dot, 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 h of x is continuous at x equals 2. So if you had, for part E, kind of a reasonable type of explanation, didn't have to be exactly as exhaustive as I made it here in answering, that would be sufficient for getting your point there. Problem 25, determine the following function is continuous for all real numbers. Justify your answer. Well, we look, first of all, if at 1 is our critical point, right? So f of, this will be condition 1, f of 1 exists and equals, well, to figure that out, we take this bottom one applies, so we're going to have 2 times 1 plus 1 is going to be 3, n equals 3. And then 2, look at condition 2. Well, to do that, we're going to have to set the right side limit to the left side limit. So left side is limit as x approaches 1 from the left side of f of x equals limit as x approaches 1 from the right side of f of x. And so from the left side, we're going to have this x squared minus 2. So we're going to have 1 squared minus 2. And from the right side, we already did that over here. We're going to have 2, we looked up this here, 2 times 1 plus 1. That's going to be 2x plus 1. So on the left side, we're going to have 1 minus 2, which equals negative 1. On the right side, we have 3. So we say limit as x approaches 1 of f of x does not exist, dot, 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 f of x not continuous at x equals 1. Okay, so in this argument, 1, 2, and 2 really foiled the deal, so does not continuous. So that would be our, I guess we can just box in our conclusion here. F of x is not continuous at x equals 1. Now, problem 26, find the value of k that will make the following function continuous everywhere. And so for that, we look at, first of all, do we have, is g of x going to exist at x equals 3? Well, yes, because we have this greater than or equal to. So condition 1 is met. So all this, we need to work on condition 2, which is left side limit meeting right side limit. So we have limit as x approaches 3 from the left side of g of x equals limit as x approaches 3 from the right side of g of x. And to do this, from the left side, we have this negative x plus 9. So the left side, we're going to put negative 3 plus 9. And on the right side, we have k times 3 squared plus 1. So on the left side, we have negative 3 plus 9 is going to be 6. We have 6 equals, we have 9k plus 1. And if we subtract 1, we're going to have, from each side of the equation, we're going to have 9k equals 5. So k is equal to 5/9. Now I should see a boxed in answer. I should see work leading up to that answer. A k equals 5/9 alone without supporting work is what we call a bald answer, for which you receive no credit. Complete the following statement. Use math notation. The limit as x approaches a, or alpha, of h of x exists only if and only if, well, the limit as x approaches alpha from the left side of h of x, it's supposed to be h of x here, equals the limit as x approaches alpha from the right side of h of x. And most who got this problem right put this particular notation. I had one student who made a verbal equivalence. If the left-hand limit as x approaches the number equals the right-hand limit as x approaches that same number. And so I gave that person credit, although not strictly math notation, it was verbalized sufficiently to be crystal clear. So that was a way you could have answered that. Okay, problems 28 through 35, using the graph of f of x, answer problems 28 through 35. Okay, we have 28. The limit as x approaches -5 of f of x. And so we go from the left side here, and we approach a value from the right side. And since we have continuity, we're approaching the same value. It looks to be maybe a vertical tangent at x equals -5, but still approaches that same number from each side, which is 0. So 0 should be our answer to problem 28. Problem 29. The limit as x approaches -3 from the left side. So here's -3. And if we're approaching from the left side, that would be this thing right here. It looks like we're approaching about maybe 1.8, 1.7, not quite 2. So I'm going to put 1.8. Now, if on your test you rounded off to 2, like you said, oh, that's 2, I would have accepted 2 as a correct answer also, or anything close to this 1.8. So that shouldn't be an issue as far as getting it right. Concept. Correct concept is what I'm looking for. Okay, 30. As x approaches 3 from the right side, so we're going to go over here to 3, not -3 like problem 29. So 3 from the right side. Okay, here's 3. And we're coming right here. So we're approaching 3 from the right side. Looks like it's not right on the line 1, but maybe a little above. So I'm going to say 1.2. Now again, if you went ahead and put 1 or anything close to that, I would have given you full credit for problem 30. Problem 31, the limit as x approaches -3 of f of x is, so we go back to -3 here. Well, the limit from the left side is 1.8. It's determined up here in problem 29, but the limit from the right side is going to be -2. And so those limits are not the same from the left and from the right. So that limit as x approaches -3 of f of x does not exist. And then 32, the limit as x approaches 1 from the left side of f of x. So we go to 1 from the left side, and here at 1 we have what appears to be a vertical asymptote. So we're going to get, looks like we're going towards positive infinity, and the limit therefore does not exist. And in 33, the limit as x approaches 1 from the right side of f of x. We come from the right side, and now the function is going down toward negative infinity, so we're going to say negative infinity, which translates to a limit that does not exist as our answer for problem 33. Problem 34. We have the limit as x approaches 1 of f of x is, well, the limit from the left side, which is negative infinity, does not equal the limit from the right side, which is infinity does not equal negative infinity. And even if they were the same, it still would not be an existing limit. So our limit does not exist. Yeah, if one or both of those things does not exist from the left side or from the right side, that blows the whole limit altogether. Okay, finally, the limit as x approaches infinity of f of x. Well, here, as x approaches infinity, we're kind of honing in, and what I did is I made an assumption, looking at the graph, that there's probably a horizontal asymptote at x equals 2. So my answer I gave here was 2. And I know that if you might be able, by looking at the drawing, assume that this will continue increasing, but this is going down as a horizontal asymptote to the right. So our answer is 2 to problem number 35. So that's going to be our entire test. I hope you did pretty well in it, and to the extent that you didn't do well in this, I hope you pay attention to everything you did to learn, because there are so many key concepts of limits and continuity embodied in this one test, plus a few other things. So with good practice on justification. So good luck in your future endeavors, and thanks for viewing.